All right, why don't we go ahead and begin? So it's my great pleasure to introduce to you Philip Kim from Harvard. So I'll give more of a sort of personal touch here. Philip is sort of one of the greatest condensed matter experimentalists of his generation. He was responsible for some of the very early work that kicked off, enormous enthusiasm about graphene. And in my opinion, as well as many others, he deserved the Nobel Prize, or part of it that was given to Geim, but that came out of my mouth, not his. Yeah. I guess one other sort of nice personal story about Philip is that it's due to his work that I'm not a string theorist. So, yeah, the first sort of What?
I said thank you, Philip.
Oh, yeah. So, yeah, when I was a graduate student at Harvard, I worked with Philip on just sort of yet another of his sort of major, well, maybe for him a minor achievement of discovering relativistic hydrodynamics in graphene. But for me, that kicked off my whole career. So anyway, he's certainly, it's my great pleasure to welcome him to give this colloquium, and please join me in welcoming Philip.
Thank you. Yeah. Thanks, Andy. Yeah. In my opinion, you're still contaminated by the string theory, by the way. Joke aside. It was my great pleasure to come back here. I think I just kind of thought the first time I visited here and gave a talk was probably 10 some years ago, and that was at the time that the graphene was still pretty hot. Single layer vanilla plain graphene was still hot, and I share some of these interesting stories around there. And things got changed quite a bit over the time, and then yet you may think that why another 2D talks, and especially then that there are many people before me also gave you that some of the exciting development in the two-dimensional materials. And I'm probably going to tell you that why that's the case, that kind of close toward the end of my talk, but okay, so let me start it. So I would say this 2D material, or the materials in the effectively 2 dimensions, as started out for some time ago. I think this molecular beam epitax is one of this important technique that has been developed in the 70s and 80s, maybe even dated back to 60s in some sense. Provide that very important material platform that experimentalists can build effectively 2 dimensions by just kind of depositing the atoms in the layer by layer fashions. And if you just control this substrate and the atom interaction, well, in the end of the day, you can grow this material really layer by layer up to this wafer scale. In fact, this semiconductor heterostructure is one of the really important platforms that modern electronics can rely on, including all this the transistors and then LEDs and those kind of things. But also for the physicists, this is a nice platform that we can study about the interesting, the effective low-dimensional physics. One thing can be signalized that in this the 2D heterostructures or semiconductor heterostructures, you can confine the electron into the effectively in 2 dimensions under the very strong magnetic field. You can create this extremely correlated state to the electron 2-dimensional electron system, and ends up with this the fractional quantum effect, which is one of the very exciting phenomena that one can see in the low dimensionalities. Right. As Mandy mentioned, some 20-some years ago, it's about 20 years ago, I guess now, there has been new type of the 2-dimensional material start kind of available to the community. It started with this single layer of the atomic sheets of the graphite called the graphene. Funny enough that back then there are a few different approaches that try to come up with this single layer graphene. Turns out a very simple method, mechanical exfoliations, fancy way to saying that using Scotch tape to cleave up the crystal, that allows us that kind of many physicists that come up with this the effectively 2-dimensional system very cheap. And not only that, in the graphene there are effectively this relativistic the electron dynamics can be realized, and this becomes kind of one of the hallmark that new type of the two-dimensional system is available to the community. But turns out that was actually just the beginning. Over the few years, now about 2 decades of the time, the community realized there are other type of the two-dimensional material. It comes around first boron nitride, then transition metal dichalcogenide. Turns out that some of the known materials, that including the high temperature superconductor, often that the materials consist of the layered material, layered system, and all this chemical bond is within the layer, but between the layer it is a weak van der Waals force kind of holding them together. So in principle, you can extract this material down to a single atomic layer, or you can grow them in some cases. But the important part is down to this single atomic unit cell, material can be stabilized. I think that's kind of very important part, such that experimentalists can now put their hands on to this material to study them. Not only that, many of these 2D materials came with a very different type of flavors in terms of the electronic properties. Some of them becomes superconductors, some of them metal, some of them becomes semiconductors, magnetic materials, and strongly correlated system, now down to the even just a strongly correlated heavy fermions. In fact, the list of the material grows almost every week, and discovery of the new type of the two-dimensional materials comes down almost every week in past probably 10 years or so, right? So there are kind of variety of these 2D materials available, but on the top of that, because of their interactions between the layers, van der Waals interactions, so unlike this, the molecular beam epitaxy growth, where that interface consideration for chemical compatibility as well as mechanical compatibility is important, here that you don't have to pay that attention too much, simply because of van der Waals, weak van der Waals interaction, which allows us to kind of build, in principle, three-dimensional structures out of these layered materials, and quickly can come up with the quasi-three-dimensional, the van der Waals heterostructures out of this combination of the different materials. And that's basically provide us a lot of the opportunity to explore that interesting quasi-three-dimensional structures. It's not the PowerPoint demonstration I just showed here. Indeed, experimentalists demonstrated one can build this type of heterostructures. In this particular case, it's a graphene in between the boron nitride, basically assembling a rather simple way of the successfully picking up by cleaving off the crystals down to monolayer. But nevertheless, in the end of the day, you get the very similar quality of these heterostructures one can build up by just MB system. But on the top of that, when you just kind of put them together, you just kind of put them together, this material with the right shape and right geometry, allows us, in fact, just selectively etch the crystals and these stacks and address of each of this atomic layer by just kind of outside the electron, which means that even though some of the crystals are very close by, 2D system is atomically close by, but we can carefully just kind of address each of the individual layer by just kind of means of this device fabrication. And that's another very important the capability we have. Especially that initial attempt made on the graphene in between the boron nitride, one can get extremely high quality of the electron gas that in this way, the mobility is approaching to the millions or tens of millions. Basically, mobility of the electron that you can achieve into the one of the best gallium arsenide crystals, which immediately allows us that, for example, that applying the magnetic field strong enough, you can get all the fractional quantum physics that has been done in gallium arsenide reappear in the graphene. In some cases, even stronger, the robust, simply because you can put much more carrier density into the graphene with high magnetic field to make this effect is rather robust. And sometimes repeating very similar physics that appear in the gallium arsenide in graphene, but in the robust way, provide us another the advantage to using this type of 2D materials for study I'm going to kind of share. For example, that nowadays that put the graphene in between the boron nitride, you get the high quality sample as you're showing here, allows the following type of the experiments. You can just kind of treat that as if that I have the semiconductor heterostructures, and you simply apply all the method that we learned from gallium arsenide, repeat it here. So in this example, we start with the stack and make the contact and make the etchings and make the local top gate structures. In this way, that we just kind of build up the mesoscopic device as if this gallium arsenide two-dimensional electron system, and applying the magnetic field, we can just put this device into the quantum Hall limits, and the way the electron is now moving only across along this the quantum edge state, and by controlling this edge state directions by just top gate fabrications, we can basically build up the device that sending the electron through the particular path, and under the magnetic field, electron goes through the specific path I just aligned. Basically, this is a device that we can make the electron version of the Fabry cavity, where that I can just kind of read up these oscillations of the interference coming from this cavity oscillation by just reading of the resistance. And this method, in fact, has been done in the gallium arsenide based on quantum Hall, the device, and often called, this is what we call the quantum Hall interferometer. And one can read it up that very nicely, all this electron oscillation. The advantage we have here is that this device is much more robust in gallium arsenide. We can just do this performance a little bit higher temperature in gallium arsenide, or even the stronger the fractional quantum Hall sets in this type of device, which will allow us to explore that the exchange statistic onto the system. So this is kind of one of example. Yes, yeah.
Can you say which, BT and I, which are the actual?
So that, okay, so this is the example that I'm showing you, so that not much of detail. What we can measure is we can send the electron through this the path, and this is a quantum point contact. We can actually divide off the electron paths into two different paths, and that some of this electron is now going there, and some of the electrons reflect back. In the end of the day, we are actually measuring that electron that going back and forth between its cavity, and we just measure that electron comes out. And basically that voltage that we are reading on the downstream is the transmitted electrons' chemical potentials divided by the current we inject will give us that basically the probability electron comes out from this cavity.
But it's the longitudinal voltage across those between
Yes,
the left
yes,
and right.
yeah. That's basically the transmitted voltages that contains the information about how the electron is interfere the inside of this cavities. This again, sorry about that. This is about kind of about micron or two. So this is a device oscillations. This is about the kilo ohms, and then what we expect here is about this is a 10% of the visibility of what we are seeing that compared with the 0 that is supposed to go. So it's about 10% of visibility. This one is basically tuned by the filling fractions, and already voltage is converting to the filling fractions. That voltage applied on the top gate, the tune this the filling inside of the top gate. So that's kind of way. Sorry about this, all the missing, because I just kind of, my intention is not to dwell on this this slide, just showing that, hey, this is a capability, we can just do that. In the same way, another the demonstration of the thing is, we can now, unlike the gallium arsenide, we can actually replace one of the electrical contact with the superconductor. And intention here that this is the superconducting electrode. Usually in semiconductor, it's very difficult to make the good contact with the superconductor, which is usually refractory metal, right? Because of short barrier formation. Graphene, there's no gap, so we can make the good contact. In this way, that we can make the close connection with this quantum Hall edge state with superconductor, which allows us to proximatize the superconducting, the quantum Hall edge state with the superconductor, and we start to see that this negative signal appears, which actually indication of so-called cross-under reflection. Again, I'm not going to dwell on the physics here, although it's very interesting. Simply, I just show you that this two example that we can actually repeat something done in gallium arsenide very comfortably in the graphene device, or even more, just rely on this two-dimensionality, the semi-metal, the property of the graphene in the system. Of course, we don't have to dwell on just one layer. You can actually kind of put this kind of rather complicated device structures here that this is two graphene layers separated by the thin boron nitride, and each of the graphene layers is again separately contact and controlled by all the gate structures, and this is kind of common device structures one can also build up with a little bit more of the layers staying there, right? We can repeat this one with not only graphene, but also, as I said, there are other 2D materials. In this particular case is tungsten diselenide, moly diselenide. One is a p-type semiconductor, and the other one is an n-type semiconductor. So you can think about this type of the contact will make this the very thin PN diode. So that's, again, that you can make this kind of rather complicated device structures. We can study about that. Again, demonstration is you can go beyond the graphene and make the complicated device structures. Perhaps in terms of the bragging, this is one of the complicated devices we just kind of made in the lab. And what you see here is in here that we have about this 9 or 10 different van der Waals layers, right? Including so-called this twisted bilayer graphene and 2 of them, and separated by the thin band. Whole point here is one can repeat this one to the many, many layers. And many of these things has their own context and make the complicated devices. But this type of the heterostructures and the making the contact of the individual layer basically allows us to bring this new functionality of this material. And that's basically something that I'm going to share together with you. So out of this, I will just kind of give you a few examples that what type of the interesting physics we can explore. So being into in the University of Colorado, I feel like that I think that I should say something about the quantum, and especially to make the connections with the condensed matter physics. I want to kind of discuss about some of the so-called macroscopic quantum state we can realize in the system. And then I should define what I mean by the macroscopic quantum state. My definition is rather mundane. Anything that I can see with the naked eyes, and undoubtedly it's a quantum mechanical effect, that I will just define out the macroscopic quantum states. And 2, the common example is the superconductors. With this kind of bulk superconductivity, you can undoubtedly see that this is some cool things going on. Or superfluidity, you can see that a lot of the interesting macroscopic phenomena can be seen. Also, in some sense, cold atom BC condensation is a good example, because if it is condensated enough the cloud, I was told that you can see this kind of cloud with the naked eyes if you have the good eyesight. So all of these things actually has something that it's not only one particle, but there are many, many particles getting to this quantum ground states. And that's kind of one, in some sense, the behind of the secret, why they becomes a robust macroscopic quantum state. Of course, the physics behind of all this thing is basically some sort of boson degree of the freedom is condensated, right? But note that this boson that we are talking about, that behind all of this thing is not just kind of elementary boson, but they're all kind of composite bosons. Some of this, the other elements, especially in some of the Fermi degree of freedom elements, actually combine together to make this composite bosons, and that's what kind of make this robustness is possible. And because of these composite bosons, in principle, you can think about if I somehow messing around that this the inside of boson, especially controlling the size of the boson, we can in principle envision that changes of the nature of this type of condensation phenomena, right? Indeed, this has been that the common theme between also condensed matter physics as well as AMO physics, that kind of spinning around that this idea about composite boson degree of freedom and condensations, right? Here's some of the old work that in physics today basically nicely try to couple that idea about the changing the size of the boson will change this the condensation natures from so-called the BC to the BCS crossover. And in fact, this has been one of the very nicely demonstrated topic in the AMO colleagues, that starting from this difermi atom molecules and controlling the Feshbach resonance, controlling the size of this boson, that one can nicely demonstrate in the AMO physics that the BC to the BCS type of the crossover has been kind of very nicely demonstrated, right? In some sense, in condensed matter physics, there has been some seeking the example that indeed whether one can come up with this idea about BC and BCS crossover. Some people think that maybe even the high temperature superconductor may kind of fall into that category, although this is a rather controversial argument. But one idea is indeed if you come up with any kind of composite bosons in condensed matter system, one may actually drive into that category. And some of the other idea is indeed, can we come up with the composite boson degree of freedom in condensed matter system? And one candidate there is, say, exciton. When you have this, the field band of the semiconductor shining the light, we know that we can create this, the exciton, or which actually combine of this excited hole from the valence band to leaving the behind excited electron from the valence band to the conduction band, leaving the hole behind. Basically, the Coulomb interaction between them from the bound state of what we call the exciton. Of course, exciton as excited state has a finite lifetime. But somehow, some with magic, if we make that this exciton lifetime is long enough, one can envision that there's some quasi, the phase diagram one can draw of this exciton. Indeed, at least in the theoretical land, people come up with the idea a very similar way that if you have the bunch of the exciton and getting to the low enough temperature, indeed you can condensate this exciton into the exciton condensation. And depends on the exciton density, especially compared with the distance between the exciton with the size of exciton, you can get into the BC like this well-isolated exciton condensation to the more of this intermingled exciton with this distance comparable to the size of exciton, more like the BCS type of the condensation is possible, and in fact it can be tunable by the exciton density, and there has been some of the discussions out there. Of course, creating those kind of system in the solid state condensed matter platform is very exciting. Also, there can be some of the experimental, it can be give us some of this applicational, the implication. The one problem of the realizing this type of the phase diagram is, of course, that important assumption I started with. If the exciton live long or forever to get this the phase, that should be the first thing we have to realize. Yes.
So at finite temperature, I mean, you draw in this phase boundary. Is that sort of schematic?
This is a kind of schematic. So this can be true phase transitions, or it can be crossover. Depends on to the system. The idea is even at the finite temperature. And in fact, in the classically, that is expected because the idea is if the exciton becomes dense, right? Electron hole that consists of exciton start to see the other electron hole, right? Eventually, at some point, all these electron hole will kind of screen each other and just kind of unbound the excitons off. And this is what is expected to happen in the Mott transitions. And experimentally, actually, people did see this Mott transition has happened into the semiconductor system. Whether this is a true phase transitions or crossover, again, this actually depends on whether I can call that as a phase, right? Because it's all the excited states. So yeah, finite temperature, finite lifetime. This can be a little bit of the arguable, but it is kind of expected to see that, and there's experimental evidence has been seen at least in the Mott transition ranges, right? The trouble here is, again, that fight with a finite lifetime. There's the outlets on this one. One way is basically, instead of just studying about the exciton per se, but we can just kind of put the exciton into the optical cavity, right? And couple the exciton with the cavity photon that create this so-called exciton polariton. And exciton polariton, as a kind of bosonic, bosonic degree of freedom, if you just pump enough this exciton, the lights in there and create these exciton polaritons in there, they tend to condense. And in fact, you can beautifully show that this exciton polariton condensations into this exciton in the cavity. You don't actually need even the lights. You can just create these cavities and drive this cavity by the electrically. You can generate the electroluminescence in there and create enough the cavity photons in there. They can also kind of still generate this exciton polariton. In fact, this is one way you can make the really nice coherent light source with this strong light matter interactions and has been explored in semiconductor heterostructures. However, in this system, it's a little bit of difficult to call these exciton condensations that we are talking about, because here that, well, this the coherence or is basically derived by these coherent lasers. So at some point you have to think about whether this is a really lasing versus a BC. There's a bit of this, depends on the point of view, you can just kind of call one way or the other, right? But then, is it really possible that I can create these similar things without any laser field? Well, there has been some directions that people has been pushed into semiconductor structures, and it was a beautiful idea and simple idea. Instead of you have the one layer of the heterostructures, imagine that you have another layer by just growing the quantum well, right? And shine the light, you can surely create this exciton in one of the quantum well, right? But then you just bias the quantum well with the external voltages and tilt this quantum well. And what can happen is that this intra-layer exciton can dissociate it, and either electron holes move to the opposite layer to form their own majority carriers and happily leave it there, right? But then there's a residual, Coulomb interaction between these two can still kind of bound them across this interlayer and can form so-called interlayer excitons in this way. if the barrier is large enough, the barrier is high and tall and wide enough, and there is a good enough separation between the electron holes in terms of suppressive wave function overlap, often that this exciton, the interlayer exciton, can live reasonably long, and not forever because there's still some finite overlap, but reasonably long, and that's already good enough to start to drive some of the interesting states. Indeed, the gallium arsenide quantum well, double quantum well, the people just kind of, for example, that this work was done by Alex High at the UCSD when he was there, that shining the lights into the system and then enough the creating excitons, the excitons start to generate the self-deriving coherence in there, which is probably the first step to start kind of develop some sort of the condensation states. However, it was a really heroic effort, but there is also kind of bit of the concerns there. Part of the reason is, although exciton lifetime is long, it's not forever. It's something like still 100 nanoseconds. And part of the reason is basically that the cavity is still kind of confined, but not tightly confined. So there's a leak out of the electron wave function or Hall wave function, and there's some of the overlap to make this finite lifetime. Furthermore, because it's semiconductor, although it's Coulomb interactions there, but all this dielectric screening of the semiconductor in the three-dimensional structures make this binding energy is relatively weak, about 3 millivolt. So this can be done with relatively low temperatures and kind of rather feeble. You cannot create a too high density, otherwise it's kind of start kind of unbinding. But this gives us enough hint, directions that we can move. So what we can do is we can just copy very similar experiments now using two-dimensional semiconductor, right? I told you that there are a lot of different type 2D materials. Speaking about only the semiconductors made out of transition metal dichalcogenide, they are quite abundant of the different type of these 2D semiconducting layers possible. We particularly choose for this experiment this moly diselenide and tungsten diselenide with band gap, with band alignment. When we just put them together, moly diselenide is N-type, tungsten diselenide is P-type. So immediately when we create this exciton and bias it, like the semiconductor heterostructure case, we expect to see that there's an interlayer exciton can form across this type of the layer, right? So that's good. Also, this is a really tightly bound to each other because it's a kind of very thin layers, and there's a van der Waals gap between that, which means that the gap here is basically you have to almost get outside of the vacuum and come back, which means that although this is thin barrier, but they are tall enough such that wave function overlap becomes kind of minimized, right? So immediately you get the huge binding energies and reasonably long exciton lifetimes here, right? So what we can do, we can make the device. I already showed that this device, I think, has one example, right? The world thin PN diode I mentioned, right? Optically, that's basically type 2 alignment. So when you shine the lights, indeed, you get this interlayer exciton forms, and you can just kind of explore this interlayer exciton by the photoluminescence. Shine the lights over the band gap and see that how this exciton is emit back, and just kind of look at that energy scale. I know that what is the interlayer exciton energy scale. And when we just put the gate top and bottom, applying the electric field, that electric field can couple with this exciton, such that I can tune even just exciton energies by simply with the gate voltages. And it's a linear stock shift of this energy will give you some nice kind of shift. But the important part is, because they are tightly bound and they are reasonably strong the binding energies, it turns out their lifetime is fairly long, and especially this lifetime can be even controlled by the gate voltage you apply. When you just kind of try to separate the electron hole within the layer, their lifetime can be as long as kind of a fraction of milliseconds. So that's kind of good news, right? And furthermore, we can not only create this exciton by putting the lights, but we can actually create this exciton by injecting the electron hole through the electrode. So in terms of the transport device, this is a PN diode, right? So when we just kind of put this the electron and holes in the opposite layer by just by contact we have onto the outside of the device, this device behaves like the diode, and this diode can be tunable by gate voltages because the doping can be controlled by the gate voltage. Especially when we just put this diode in the forward biasing, device start to emit the lights out of it, right? So this light is a recombination of the exciton that I just create by the electron injections. And in some sense, I can just look at this exotonic states by just light coming out from this device. Yes?
Should there actually be steps in the lifetime as a function of behavior?
Yeah, well, I think that it is like the behaviors. In fact, if you just look at there, that whether it's intrinsic and that kind of getting the more of the charge regime, there seems like that there is some kind of discontinued behavior. I'm not sure whether I can claim that step is here, right? But anyway, so that's
Not expected, right?
that is not expected. Yes, yeah, yes.
You talked about applying more or less a DC field and rotating the entire potential surface.
Yes, yeah.
Have you thought about applying a very strong IR laser, basically rocking it back and forth?
That's also kind of possible. I think in principle that you can just do this in a more dynamic way, just kind of applying the another way. We didn't do that, right? I'm a transport guy, more like this is already sophisticated optical experiments we can do, but I think that's kind of an interesting idea that one can explore.
Use the high harmonics generated to
Yeah.
kind of look at things in real time and make it
Sure.
show.
Yeah, that's that. I think that interesting things one can do. But here that you can see that, all right, so it seems like that we can generate a reasonably long-lived interlay exciton. There's actually even further efforts was done in this community. Few years, I think, around the similar time, our colleague or the competitors, in some sense, at Cornell, actually demonstrated even cool kind of demonstration. Here in this the group done by the Kim-Fai Mark and Ji-Shan, make the very similar device I showed you, but they actually go one step further. Instead of they making this PN diode I just made, they just kind of slide a very thin layer of this boron nitride in between. So make the separation further, right? By just doing so, they have this disadvantage because they don't get any more of the light directly coming from this the exciton, interlay exciton, because now their lifetime is even longer, and there's a very small opportunities they recombine give us light, but external lifetime becomes quite kind of longer, right? And that what they see that is they just kind of using these electrical hole injections and make the tunneling regime. And tunneling current shows a very strong singular behavior, especially that there's a nice cusp appears a tunneling current. It turns out the detailed analysis tells us that the tunneling current is associated with same amount of electron hole injection in the system to make the sharp cusp in the transport is a good indication indeed to say there's something interesting going on. And furthermore, let me skip this part, but the important part is here. They measure the quantum capacitance of this tiny the capacitor they made, and they start to see that when they just put the equal number of the electron hole in the system, there is the signatures they can measure in the quantum capacitance. There's some of the bound state and gap opens up actually happens. The many-body state gap opens up, an incompressible state, the strongly compressible state appears in their signal, again indicating there's some sort of the indirect evidence of the condensation start appears even at high temperature up to 100 Kelvin. So that is very encouraging, right? So the next step that we want to do is, can we actually just do this one really directly? Just can we measure coherence directly in this measurement? So we actually kind of copy the experiments and just kind of combine with the IO experiments and kind of take the in between in the following way. So we now just put that very thin layer of one layer of the boron nitride in between them. And the idea is we want to make the lifetime is kind of longer, but nevertheless, still it allows enough the light comes out from the interlay exciton such that we can directly observe how the interlay exciton, the emission should comes out. In this device, you see the interlay exciton formation, but the important part is when we just look at this, the tunneling current measurement, indeed you see that this sharp cusp appears, what they see in the tunneling resistance appears in this device. That's good. But when this cusp appears, that when we just inject the same number of electrons and holes there, we can also see that there is a light comes out in this system, in that condition, in the spectrum. This is now no lasers, it's a completely electroluminescent, right? And that light is a threshold turns on. And at least when we just measure this G2 of the photon emission, we start to see that there is some of the G2 correlation appears right before that threshold turns on. But when the light is kind of really intensely turn on threshold, the G2 actually collapses down to the 1, right? So maximally, that hopeful cases, this might be interestingly related with something like the developing coherence in there. The indeed coherence appears that with this G2 equal to 1. Well, it's a maximally hope that indeed one has to demonstrate indeed there is a real coherence appears in the spatial and time resolution of the study. This is one thing that we are going to do that. Unfortunately, our initial assessment, it seems like that this G2 collapse may not relate with the real coherence development at this point. But in a sense, the struggle that you see here is we are trying to make the finite lifetime exciton as if that is long-lived, and we have to drive the system to kind of build up the coherence without any laser coherence. That is kind of really tough things that we have to do, right? So you see that it's tough, the game we are playing. While that, I feel like that there is still room that we can just kind of push this one. But I can just kind of spin these things a little bit kind of different direction. There's a yet different way that we can turn around this problem. And just to demonstrate, indeed, we can still create exciton condensation by solving the problem that we inherently have here. The inherent problem we have here is we are working with the excited state, right? So can I just kind of walk into the ground state to realize this? Yes, Len.
Yes, I was going to ask just connections with like Eisenstein's old experiment
Yes.
with quantum Hall bilayers.
Yes.
So do you expect here, I would expect here that there would be zero bias peak if you have
Right.
a very low tunnel.
Right. The problem here is that this is a driven system, right? In other words, basically, I have the bias to inject the electron hole into the system, right? So that's why that there is nothing that what you're saying that Eisenstein experiment, which I'm going to discuss in a moment, right, cannot be done here, right? So the limitation we have, the working with this one, since that in some sense, if indeed this exciton is turn into the condensation such that, and then we can just see the light coming out, that is a really direct proof, see the coherence. This is nice, but technical difficulty we have is this driven system, that how we can just stabilize this one into quasi that condensation. It's not the ground state.
Lifetime.
Yes.
And kind of
Yeah.
approximately looks like
Right.
some effective chemical potential.
That's right.
acid effective
That's basically the way that Cornell group's experiment that just slide in the thick boron nitride. Now I just don't make this extent the recombination at all. Then I can just make those kind of things quasi-infinitely long exciton. Right. Downside of there is now I don't get the light out of from exciton. Right. So that's kind of, so to prove that for the coherence, I have to go through a different way. So that's actually kind of related to what I'm going to discuss now. So as Leo mentioned, in fact, there is a way that we can realize this exciton condensation in ground state. And that was beautifully done by just replacing your semiconducting gap with a Landau gap. So imagine that I have this tool, again, that the system, electronic system, right? But except that here, that I just rely on that this band alignment, simply apply the magnetic field and ask what happened. Of course, under the magnetic field, cyclone orbit is quantized, and I always see that there's the Landau level forms. And of course, if this Landau level is fully filled, then we know that there's a quantum Hall effect appears, right? But imagine that instead of I fully fill the Landau level, I leave the Landau level partially filled. Now, typically, that unless there is a very strong correlation, this partially filled Landau level is not so exciting because it's kind of in terms of the conducting property. Partially filled Landau level is bad matter, right? But in the special case where these two the layers are small separation, but partially filled in a sense they're complementary filled, and then you can expect kind of interesting things. If they are very close by, eventually if I just kind of project them into the one layer, right? Because this is the complementary field as a two layer as a one, this is a full Landau level, and I expected the quantum Hall effect appears with this edge state conductions as I just mentioned, right? But if we just look at them very carefully, right? Still this two layers a small separation, then if one layer electron is there, that will expel the electrons underneath. That hole is likely underneath. Therefore, that you see the electron bind with the hole underneath, right? So in a sense, this is one way, or hand waving arguments, but create this the interlayer excitons form under this magnetic field. Often we can call this as a magneto-exciton formation. In fact, there is a really nice mathematical structures kind of completely prove that by just kind of write down the wave function in the quantum Hall effect with consideration of this two layer of interactions, that the mathematical expressions of the weird quantum Hall state is exactly follow through the same mathematical expressions that you expect if the exon is live forever. The condensation state can be written in the very similar the wave function form. So it is not only analogous, but there is a kind of nice, interesting the mathematical mapping is there. As Leo mentioned, this experiment was briefly done already about 30 years ago, right? So starting from the beginning of the 90s, the Jim Eisenstein group at the Caltech made a series of the experiments and improved this experimental technique, and indeed show that indeed those kind of the magnetic condensation state can be done. And one way you can beautifully demonstrate, there are many different ways, that one way of the beautifully demonstrate that exon condensation is following way. If the exciton as a boson condensated, exciton move like the superfluid, right? So there will be no exciton, there will be no energy dissipation you expect when exciton is moving. Electrically, it's very difficult to measure because exciton is charge-neutral object and the current is carried by these charges, right? But there's a clever way that you can measure that. Say, if I have this two layer and I couple this two layer that at the end of one of the sample and send the current here and return the current in the opposite direction. So this is what we call the counterflow current geometry, right? And imagine that I have the holes here, electrons there. If the current is flowing here, hole is flowing through this direction, right? But the current is now returning there. The electron is then flow also the same direction of the hole. Now that's a geometry where the exciton is binding together tightly and the superfluid condensation. And in this geometry, you expect to see zero resistance. And this is a weird case, right? Each of the layer, if you measure separately, it is bad metal. But if I just connect that, return the current, suddenly you get the zero resistance, almost like the supercurrents flow, right? So that's basically experiment that demonstrated and beautifully showing that indeed this condensation state can be realized in this the case. So what you can do? I mean, it's been done already 20 years ago, right? Well, so why not just kind of, you know that you see that I'm not too imaginative guy already. You see in the previous example. Let's copy the same thing on the two-dimensional system, right? Here that I already mentioned, graphene has a very high quality like the gallium arsenide. Simply I make this two graphene layer with separation of boron nitride. I just kind of really copy the experiments and do that. What is the point of doing this experiment, right? There's one important point. Electron is tightly bound again into the graphene layer compared with the gallium arsenide. I just put these two layers very close by, right? Therefore, exon binding energy is much higher. In fact, the exon binding energy is almost order of magnitude, even 2 order of magnitude higher. So what previously done in the Caltech was done in the tens of millikelvin. I can do Kelvin or 10 Kelvin, right? Or many theorists come back, oh, temperature is at that one scale. It's not a new physics we are doing, right? But there is one important part for the experimentalists can do. Because it's comfortably high temperature. In principle, I can map out the phase diagram I was talking about. And that's what I'm going to show you. So in this experiment, we have this graphene double layer. I just put this new total equal 1, which means each of the layers is partially filled, about half filled, right? And then keeping that condition, I'm going to change my magnetic field and the temperature, and that's kind of basically, and showing that how the counterflow resistance got changes. And this is phase diagram. I told you that when exon condensation is happening, counterflow resistance goes to 0. Indeed, the low enough temperature or magnetic field I measure within this range is counterflow resistance is kind of very close to 0, right? And as you go to the higher temperature, the counterflow resistance becomes finite. So what you see here in the color map, which show the counterflow resistance, there's a nice kind of phase kind of transition like the diagrams there, right? You see that already. This is kind of similar to that phase diagram I showed you before, right? Turns out magnetic exciton, distance between the exciton is basically controlled by the magnetic field, right? So this condensation state, as I'm just changing the magnetic field, I can see that I can change the density of the magnetic exciton. In fact, actually, I can show you that that at the fixed magnetic field, how the transition is changing, and from the low magnetic field to high magnetic field. transition behavior from the uncondensation to the condensation is kind of rather changing. But note that in high magnetic field, when we measure, this counterflow resistance will stay finite, but turn into the kind of zero counterflow resistance state. If I just call this is not the counterflow resistance, just kind of resistance, what does it look like? It look like the superconducting transitions, right? Indeed, if you just kind of look at it very carefully and analyze all this behavior that which I'm going to skip through, you can show that here that the transition is almost like the BCS like the transition. Here that transition is almost kind of like the BEC type of transition, which is kind of expected because the distance between the exon, magnetic exon, is tuned by the magnetic field. Here, basically, distance between the exon is large compared with the layer separation. Here, the distance between the exon is really kind of the close, and where that you just kind of drive more of the BCS type of the regime. So in a sense, this is a nice way that we can demonstrate it, that the phase boundary can be the map it out in this type of the system, right? Now, one can actually push this idea further. Maybe you can see that. You see that this is an interesting idea, but it doesn't look like it really smells like the exon condensation, because in a sense you are talking about some weird the quantum Hall effect, where that still you have this all the edge state which carries around. So how do I know that whether this the zero resistance state kind of I measure is simply this the dissipation state appears into this quantum edges, right? In some sense, this you can view that exon condensation, but this exon condensation is more like the topological exon condensation, exon insulator, such that edge state can be exist. Well, if you just don't want to use this fancy concept, we can actually directly show the following cases. What if I just create the electron like the Landau level and hole like the Landau level, and actually couple them to make the exon condensation, magnetic exon condensation? In this particular case, because I'm coupling the electron like the Landau level, hole like the Landau level, I don't have any edge state anymore, right? And this turns into the true exon condensation state. And we can realize in the following way. I'm showing you my phase diagram of the top and bottom layers with the wide ranges, including the electron that I showed you, or actually electron I showed you here, that's kind of nu total equal -1 I discussed before. But I can just move my interest into the other layers, something like this. This is nu total equal 0, which means that indeed I'm coupling the electron like the Landau level and hole like the Landau level. The first thing you can see that is, if I just measure individual layer, they are all kind of showing that this is insulators. Basically, there is no conduction happens, and when I just put up there, and this is a really, really nice insulator. However, if I just kind of make the counterflow resistance, this becomes kind of superconductors, right? Not the superconductors, perfect conductors, that basically there is no resistance in there. Even cool experiment we can do is following experiments. It's excellent insulator. But instead of counterflow resistance, which we measured, it becomes 0, I can send the current to one of the layer. Send the current to one of the layer. And I told you that, well, each individual layer is insulator, so which means I cannot send the current through this layer. But current can be sent into the layer if I shorted out the other layer, right? And in that cases, I just kind of send the current, suddenly current start flow, and the other layer start kind of getting the current on the same direction. And if you measure this current flowing to the other layer without any driving force, right? That current that I can just kind of send into the other layer is the same amount of current I just kind of send the top layer. This is kind of, one can say, the perfect current drag, which is kind of similar to what I mentioned about the zero counter resistance, flow resistance, and indicating that indeed once you get into the ground state exon condensation, you can just do the very cool things by just moving around this exon. That's kind of the another things that we can say. But actually, this story can go even further. I mentioned that, all right, so the partially filled Landau level is boring, but I was completely wrong in that statement, because once you get into the extreme quantum limits, in other words, a very strong magnetic field, low enough temperature, and there is a strong correlation that appears, and the fractional quantum effect appears. Indeed, in that regime, if you very look carefully in this strongly the quantum limits, although in this diagram I just mentioned, there's nothing interesting appears except that this action condensation in this the complementary field, that was not correct. If you get in the quantum limits, that's basically this region that I was talking about. Nearby, there are rather complicated things that appears, and very the careful analysis of there, you can see that there are the drag effect appears in everywhere, and especially that can be understood combining either composite fermions with interlayer flux the sharing, or even that the special cases that nearby composite fermion where the anion excitation is there, you can start to see that these two anion into the different layer start combined together to make the weird bound state. Now I cannot call that is exciton anymore because it's not a charge neutral, and there it's not a boson anymore because the anion itself is now not a fermion, no boson, and those kind of combined anionic state has their own interesting the quantum statistics, which actually a very exciting object that one can study. And you see that this becomes a extremely rich space one can study about things kind of going on in this type of the system. So that's kind of another thing that you can see that once you combine that the heterostructures, even with the two layer, we get very exciting new things comes around. Right. And speaking about 2D materials nowadays, of course, you cannot kind of avoid about talking about this so-called twist runics, right? Even just kind of not in getting the heterostructures, even same layer, single layer, once you twist it and stack them together, which is completely possible because of this the van der Waals natures, you get this yet different type of the degree of freedom you can engineer in, which is basically this moire periodicity. Of course, this moire periodicity is not true periodicity, it's quasi-periodicity, but nevertheless, this will give us the way that we can engineer additional degree of freedom in the system. In fact, around already in 10 years ago, putting this graphene onto boron nitride and similar system, people start to see that this moire structures appears in between very similar the van der Waals structures, and applying the magnetic field, for example, you start to see that so-called fractalized the spectrum of this the quantum or physics often called this the Hofstadter's butterfly problem. But perhaps most exciting development happens about 5 years ago, exactly almost 5 years ago. Pablo Herrera's group at the MIT demonstrates some weird phenomena. So what they did is they put the graphene onto magic angle 1.1 degree, and they see that graphene suddenly turn into the insulator. But then, when they actually dope this the insulator, which are not supposed to happen in the single particle pictures, then graphene turn into superconductors. And this superconductivity seems like that what you would expect is deeply tied with this flat band appears into the so-called this magic angle, right? And that basically shook this the 2D the material communities. Ever since the studies, the field actually exploded. There are many groups that kind of drag into the field that try to understand that all this weird phenomena appears, including superconductivity, magnetism, the Chern insulator, even fractional Chern insulators, and not only just that kind of this the 2-layer that the study get into 3 layers, 4 layers, 5 layers, not only single layer graphene, bilayer graphene, and just that kind of transition metal dichalcogenide, and that this kind of study actually explored in this field, basically try to give us various different type of the system by just using this twisting that provide us somewhat different engineering capability to turn into these materials with rather different from starting from the single layer. And that's kind of one thing quite exciting. Even in this transition metal dichalcogenide I mentioned, twisting start to give us that engineerability of the not only charges but the exciton, and there are a lot of interesting studies out there. But I want to end my talk with the different opportunities. That the last example. It's not only that all this system, that relatively simple system, we can just start with, make the heterostructures to make the kind of things exciting. It can be actually applicable to the rather complicated systems, such as, say, higher temperature superconductor, Cuprate system, which has been around into this condensed matter physics community about 40 years, and there is still a lot of things has not been understood, can be benefited by just kind of using this the extreme 2Dness as well as something like this. We have the degree of freedom to put them into different angle. So in this last example I'm going to share is following. So we can start with one of the high temperature superconductors. It's bismuth, strontium, calcium, copper oxide. The name itself is very big, long, but it is a really nice layered system. In fact, it has the one of the nice cleavable van der Waals layers in the crystal. So one can, in principle, cleave this crystal and study about their single layerness, but also you can just kind of put them together. The simplest the heterostructure you can make is basically cleave them, put them together with a twisting angle to make the sum of these twisted structures, right? If you just do it right, as you see in the cross-sectional TM images, in this particular sample, we just kind of put this the twisting angle at the 45 degree. And I'm going to explain the why 45 degrees is really special. And as you see in the TM images, if you just do it right, interface is extremely clean, right? And this type of crystal or this type of the structures can never be made out of MB because the compatibility of the interface, but nicely can put them together in this technique. And one can see that in this type of interface, if you measure Josephson current flow, some of the amazing things. For example, that you start to see that this nice Frohnhoff patterns appears in this type of Josephson junctions, whose periodicity cannot be explained by just simply just looking at the structures alone. Moreover, when you shine this microwave, you start to develop this so-called fractionalize the Shapiro step, which only can be explained in terms of there's a special things appears into this interface, the degree of freedom. Turns out this 45 degrees is very special, the part, let me just skip this one, because there that if you have the D wave, the nature of the wave functions, at the 45 degree, you can maximally misalign these two superconducting order parameter. At the interface, you expect to see the D plus ID type of this the superconducting order parameter appears. And as you see that D plus ID has the complex conjugate the pattern D minus ID, which is a time reversal symmetry connected. So in a sense, the superconductor interface, once you just put at the 45 degrees, basically create this time reversal symmetry broken, potentially spontaneous time reversal symmetry broken, the superconductivity at the interface. And this type of the experiment I'm just showing you is a way that we can probe those broken time reversal symmetry superconductivity in the interface. So what you see here is basically expanding that the system to the various things. We start to explore the very interesting physics there. So let me just end my talk following statement. So this is a kind of some of the slide I prepared some years ago, and that's kind of beginning of the part that the community realized that we can make this a single layer of the two-dimensional system. Not only that, we can stack them together to form this heterostructure is possible. And we immediately come up with, all right, funding agency, look, these are the materials we can just get it. And you see that in between interface, very interesting physics we can explore. For example, superconductor tied with the magnet. We know that superconductor, typically S-wave superconductor, doesn't like the ferromagnet. So we can ask, what happens in the interface? I think this kind of the interesting problems. So argument is, well, we have a lot of interesting phase space we can explore, right? Out of several years, we see that those kind of things, many problems we just kind of propose got solved as a community, right? But you start to see that the list is increasing almost every week. As I said, new type of materials appears. But on the top of that, basically we can set up another axis, that another material, you don't have to solve in two layers. You can just, how about the 3 layers and 4 layer? The axis becomes kind of many multi-dimensions, right? So we can quickly get the infinity many possibilities, a large phase space. But wait a minute, this is still countable, right? But we forgot that set of the another axis, right? So basically, we can just put the twisting angle, which can be continuously changes, right? And what you see here is the phase space we need to explore is now it becomes even uncountable. It's continuously varying, right? In some sense, that's kind of one of the excitement in this field. There are a lot of the system one can relatively quickly create it, and yet physics problem we can explore there is unbound. I think that's kind of very exciting things. And that's basically the end of my talk. And thank you for your attention. And thank for my groups that allows that this talk was possible. Thank you.
revisiting that question I asked about this interlayer tunneling piece.
Yeah.
In these last set of systems you talked about.
Graphene
you
system.
can't define, not the counterflow, which is very beautiful, but
Yeah.
the zero bias peak.
We didn't see that, and there's some reasons for that, because tunneling current is very strongly suppressed because two layers are rather misaligned, and the layer thickness is thick. But nevertheless, that is not a good answer, because say, in some sense, if it is completely coherent, right, that you expect to see that there is still kind of the coherence will drive the current there, except that if it is really the non-coherent tunneling is strongly suppressed, the coherent peak is extremely sharp, which is probably not easy to detect unless we just do the spatial decay. So at this point, the experiment, we didn't see the coherence peak appears there, unlike the gallium nitride. We didn't look for it yet. Yeah, because to look for that such a sharp peak, so we need to do a little bit more care.